Alright, so here we go. Let's use this to solve an ODE. So we're looking for a form like this. Well, let's rewrite this. We're going to write it in a form of where we can just do some direct substitutions later on. So I want to look for some function m in terms of x and y times dx plus some function n in terms of the variables x, y times dy is equal to 0. So right up there, I've taken this and I said this partial of f in respect to x, I'm going to call m, and this partial of f in respect to y, I'm going to call n. Remember, our partials are we take the derivative, as we would normally, only in x. We take the derivative only in y. The other variables we treat as a constant. So, this and this are analogous, or not analogous, they're holding the place for the partial of f with respect to x or y. Hold on here. Sure, with respect to x, yep. Plus the partial of f with respect to y, dy equals 0. And so these things are holding the place for it. Now, what's nice is, this being a differential, I can integrate in terms of x and y to get back to my f. And that's what we're going to hope for. And in the end, that is the derivative of my function that I'm hunting for. And so this is the function I'm hunting for. So we're holding place. And so once we find this, we'll be able to find my function that's equal to some arbitrary constant. So to make this work, and kind of the proof is, the first thing we have to do is we have to figure out if a function in this form is going to be exact. And a rule we're going to exploit in the proof, we don't have to do this, is if I take the derivative of x, of the function in terms of x, and then I take the derivative in terms of y, that is the same as taking the derivative in terms of y and then in terms of x. The symmetry. I normally have written these like this. And so the order of the partial derivatives do not matter, and they end up equally. You'll find in thermodynamics, where you have variables, many variables across your system state, from pressure, volume, temperature, that this set of rules forms a relationship called Maxwell's relationships. Is this idea that the order you take the partial doesn't change the value. Well, we're going to use that here to help us, because I have this dx df, and I have this dy df. So if I come over here and I take dy of this, okay, so if I take dy of what I've already taken dx with, so taking my partial in terms of y only, or taking the derivative of m using y, well, that's going to be the same as f of xy, because I'll do my x first and then my y. And if I come over here and I take the partial in terms of x, that's going to be taking n in terms of dx. Well, that's going to be the same as, well, I did my y first. Hope you can see my cursor bouncing up and down. And then I did my x. And this lets me say that the partial of whatever my m was in respect to y should equal whatever the partial was with respect to n, or of what n was with respect to x. Sorry. I was trying to think of my next sentence here, which is what we're really saying is if these two functions came from the same master function, and I took the partial of x to make this one, and I took the partial of y to make this one, if I come and take another partial of the opposite variable for them, my answer should equal. And so this is my test for exactness. And so I'm going to use an example of testing for exactness. And so what we're doing is we're building the proof of why this works. I've made some function, I took a partial of it in x. I took a partial of it in y. If I add them together, they're 0 because they have to make this constant. Well, if I take another partial, the two answers should equal. They should have the same behavior. And that's going to be my test, because if I made this function like this, so I want to test it. Well, let's look at an example of this. And this will be the example I use throughout. We'll just test it here. So my example is going to be, I have some function 2xy plus 3 times dx plus x squared minus 1 dy is equal to 0. So using the form m of xy dx plus n of xy dy equals 0, then in my m of xy is going to equal the 2xy plus 3. And my n of xy is going to equal x squared minus 1. So I want to test these. So I want to take the derivative of the m part. And what I'm looking at is the thing that sits in front of the x. I have to take the derivative of the opposite. So I want to take the partial derivative with respect to y of m of xy, which is taking the partial derivative with respect to y of 2xy plus 3. So what I'm doing here is I'm taking the d dy, not the d dx. And so of y, this is 1, and so this becomes 2x, and the derivative of a constant is 0. So I get 2x. And so my partial with m with respect to y is 2x. Now I come over here, and I want to take the derivative of x, because this was the part that was hanging out in front of the dy. So I take the partial of this with respect to x. And when I come through, the derivative with respect to x is 2x, and the derivative of a constant is 0. And so my partial with respect to of n with respect to x is 2x. And indeed, my partial of m with respect to y is equal to my partial of n with respect to x. This is exact. And that's my test for exactness. And it lets me move forward. All right, we're going to go back. On the next slide, we'll prove that these are solutions. I now know they're exact. I'll prove their solutions. And we do that by integrating back up to the function. Well, that proof of proving their functions is also the technique. Because remember, we are looking for functions that satisfy exactness. We have made the idea of exactness. Now, by proving exactness works, that method will be anything that is exact. will work its way back up to the function. And that's how your book walks through it as a proof. But there's our test for exactness.